Hi everyone. I'll just introduce you very shortly. Thank you for coming to today's seminar. Today's speaker is Dr. Sarkar. He did his PhD at the National University of Singapore, on the topic of interactions and interface of 2D molten sulfides and transition metal oxides. He then did a research fellow position from 2019 to 2021, also at the University of Singapore. And now from 2021 up to now, he is a research associate at the University of Cambridge. And he will tell us today what he's doing right now. Please.
Good morning, everyone, and thank you so much for the introduction. It's really a pleasure to be the first time in Croatia, and thank you, Nives, for the invitation. And it's a wonderful opportunity to talk about my research to all of you here. I'm going to briefly introduce myself because I'm sure he did a very good job, but just talk about my research, what I've been doing since my PhD. I have mostly been interested in looking at two-dimensional materials and how to improve or monitor or modulate their electronic and optoelectronic properties. And I believe there's a lot of interest in this institute in this regard as well. As it was mentioned, I did my PhD at the National University of Singapore with Professor, and there I worked with Professor Rekki Venkatesan, who works on oxide-based materials. And during my PhD, I was looking at how do interactions take place at the interface of materials like transition metal dichalcohylates like MOS2 and oxides like STO. And we looked at very interesting interaction between phonons and excitons in these materials. And also, I briefly worked with Professor Soumya when she moved to the National University of Singapore. And we were looking at defects in a material called hexidable boron nitride. This is an insulator, which is rare. And these defects are quite interesting because they have single photon emission and they have also spin states. So they're analogous to defects like nitrogen vacancies and diamond. And I moved to Cambridge in 2021 towards the end of the pandemic in Professor Manish Chowala's group, where I'm looking at devices because I felt that 2D materials have very interesting properties electronically and optically. But when you make devices, these properties really deteriorate because device engineering plays a very important role in harnessing these properties. And right now, I'm working at how to improve injection of spins in 2D material and looking at what factors we need to take in mind when we make devices based on these atomically thin semiconductors and semi-metals and also insulators. So just to introduce why am I doing this? Because we are living in a world today which is heavily reliant on data. And I'm not sure, do you recognize, can you guess what this is? This is a power plant, which is a nuclear power plant. And the context is very interesting because this is the nuclear power plant in Pennsylvania in the United States. It's in Talon. And this came into news earlier this year because Amazon purchased this power plant. Because the Amazon requires huge amount of energy to run its data centers, and it's not sustainable to rely on the grid. And they're trying to beat their targets for net zero, and they feel that purchasing a nuclear power plant, a 980 megawatt data center can be run independently by this nuclear power plant, which tells you how much energy we are consuming to process data. And to give you some context, where is this? Why do we need so much energy? Why do we need so much data? This is a plot very recently in a journal by some people in University College London, which showed the evolution of computing performance. So we have computers and we process information, we process data. And this shows you what is the increase in the computing performance in petaflop. One petaflop is 1,000 trillion calculations per second. And it shows you that there was a linear increase to 2010. And after like around 2012, 13, something happened which is called GPU. I'm going to tell you what a GPU is. GPU is a graphics processing unit. People who used to play games on computers earlier might have been familiar with this term, but nowadays it has become very mainstream in computing. And the rate was initially doubling. The rate of increase of computing performance, which is amount of data you're processing, was doubling every 24 months. With the advent of GPUs, it has increased to every like 3 to 4 months. And around 2019, 2020, or around 2022, with advent of something called generative AI, which we are now using like GPT, to just generate, before AI was predictive, it could predict things, but now AI can generate models, AI can generate data. The data processing is doubling every 2 months, which is like a really massive enhancement. And to process so much data, you need a lot of energy. Now, how can we process so much data? What is the backbone of this entire data processing industry? And I found a very cool image on the internet which shows like data centers. It's not like airlines or like the railway industry. It's like data centers, which is causing a lot of, it's directly responsible for emissions now. And one of the industries which has really boomed out of this is NVIDIA. You might read news that NVIDIA had a 262% jump in their profits over like last year. And this is because they are a sole supplier, or not sole, but they are one of the leading suppliers of something called GPUs, graphics processing units. And what is a GPU? So we all know what's a computer. We have CPUs in computers. In computers, we all know about like processors, and we have quad-core or 8-core processors. In GPUs, you just have parallel processing. You have a lot of these processors, which means that you are not improving the performance of individual processors, but you're just adding more processors. You're doing parallel processing. And this is enabled by using a lot of transistors. So this is an image. If you just Google search GPU, you'll get this image. And this does not look like a transistor. This just has 2 fans on it, because this shows you that the biggest component in GPU is fans, because you need to cool your GPU down, because when it is processing, it is generating a lot of heat. But if you look at the processor, it looks like this, and it has around 50 to 100 billion silicon transistors. And silicon is very important because we know that entire computing industry is based on silicon, and there's a reason for it. It is not that silicon is the best material. I mean, you might ask people, they will say silicon is very abundant. You can process it very easily, but it has all to do with the technology of how silicon transistors evolved over time. And I'm going to take you, and we need to really understand how silicon transistors evolved. I'm going to take you to the early transistors. Now, transistors, so GPUs are made of transistors, and transistors is a semiconductor device which makes electronics. And early transistors were proposed in the 1930s. These are 2 very important people in the transistor field, J.J. Linnington and Oscar Thiel from US and from Cavendish Labs, who originally proposed the transistor in the 1930s. And they said that a transistor can be a device in which you can use an electric field to control the transport in a semiconductor. It was a theoretical patent, but it was not realized. The patent was in the 1930s, but people were working on it for 20, 30 years, but nothing could come out of this electric field control device. And the main reason was it was very difficult to control transport using electric field, because you could not grow uniform surfaces in those days. If you want to control something by using electric field, you need electric field over a uniform surface. But fabrication and growth of thin films had not developed in the 30s, and you could not grow and you cannot really electric field control a device. So rather, very smart people in the Bell Labs, Walter, Shockley, and Bardeen, what they did, they tried to control transistors through current. Sourcing current uniformly was something possible. And they made a transistor called the bipolar junction transistor. And they are credited as the inventors of the transistor, but this is not the transistor we use today. We use something called a field effect transistor, where you use electric field as the input. What enabled field effect transistor was the ability in materials engineering to make good surfaces. The breakthrough was silicon oxide passivation. So a guy called Dawan Kang had this patent in '63, where they showed that you can grow very nice silicon oxide on silicon. And that is an ideal dielectric interface with silicon, semiconductor, silicon oxide, and across which you can apply a uniform electric field. Only after this discovery in '63, we started having field effect transistors. What this tells us that it is not just the material, but also the material processing techniques, which play a key role in enabling a material in a device. Because you have better materials than silicon in terms of electron mobility, but silicon has been lasting for the last close to 50, 60 years, because we have optimized the techniques close to silicon. And I spoke about transistors. This is, I think you can close your eyes, you know transistors, but like this is very basic. Like, what is a MOSFET? MOSFET is a metal oxide semiconductor field effect transistor. And if you look at a textbook, it looks like this. This is a figure of an N-channel MOSFET, which is carrying electrons. And you have a device where you have something called a source and a drain, which actually sources electrons and collects the electrons, and you have a channel. And you have a third terminal called the gate. And by applying electric field across the gate, you can change the Fermi level of this channel, and you control. And if you have an NPN junction, you can imagine it will have some depletion width because it's a PN junction. And with the gate voltage, you modulate this depletion width. and you can control the flow of carriers from one terminal to the other terminal, and you can switch off the device or switch on the device by applying electric field. This is a transistor. This is, I mean, you must have come across this in your semiconductor physics lectures or early on. But what is interesting to know here is that what are the materials involved? In a basic silicon transistor, we have, if you have N-channel transistor, you have a P-type silicon with a doping level of around 10 to the power 17 per centimeter cube. You have source and drain with a doping level of 10 to the power 20. And the doping level is very important because silicon is a bulk semiconductor which you can dope. You have techniques like ion implantation. You can use high energy ions to implant boron and nitrogen. These act as impurities, and they dope the silicon into electron carrying or hole carrying. The gate oxide, as I discussed, was passivated. It was ideally realized to be silicon oxide, and you have polysilicon. So years and years of materials engineering have enabled transistor, which is helping us do everything today. So the key thing to realize is it is not just the discovery of materials, but the discovery of techniques which are compatible with the material that will only enable a device out of the material. Now, what's happening is we are now scaling down materials. As I showed in the graph before, that we have 100 billion transistors like jammed inside the small device, which has shown that how materials engineering has helped us reach transistors which were microns in length to maybe 50 nanometers. But as we are getting smaller and smaller, we are having problems because as we are reducing the size of the transistor, we are also making them thinner. And as you make them thinner, surface effects are starting to play a huge role. So, for example, in 3D materials, you have dangling bonds. And if you make them really thin, then these dangling bonds often act as scattering centers and affect the mobility of carriers which are moving through this channel. 2D materials are quite promising because they are atomically sharp. You have no dangling bonds. And this is a plot which shows how does the thickness, as you reduce the thickness, what happens to the mobility of carriers in a material. And you can see these materials have reasonably high mobility at even lower thicknesses. And because the carriers are kind of confined, you can in principle control them very well with the gate because they're not distributed in the whole three-dimensional bulk as is in the case in silicon. And what motivates us is very recently, this field has been there. The first transistor based on a 2D material called MOS2 was demonstrated by Andres Kiss in 2011. And it is 2024. It has taken 11 years or 12 years of work for finally like industry to kind of take it seriously now. And TSMC has been recently starting to develop MOS2 transistors. These are proof of concept devices, but still we have been able to convey that these materials can be important if you want to consider logic and memory devices which are extremely ultra scaled down. Now, I want to talk today about like some of the challenges with 2D transistors. So the key message is that this technology has moved from proof of concept one device in the lab to hundreds of devices on a wafer, but there are still some challenges that remain. And the key challenges are these materials are still riddled with defects. What we do in the lab is we use Scotch tape and we open a crystal up. And even when you have, even if you use crystals which are purchased from like H2 graphene or like commercial companies, you have defect densities in the order of 10 to the power 12. But to have compatible, like really high performance, and what these defects do, they often like move the Fermi level from the middle of the conduction from the band gap to either close to the conduction band or close to the valence band. So like there's a very common material called MOS2. And if you ask everyone in the community, they will say MOS2 is N-type. But no one knows why the MOS2 is N-type. There's no reason for it to be N-type other than defects or the contact which pins the Fermi level. So we really need to reduce the defect density to around 10 to the power 10. And there's been some work using flux growth, which has enabled this. Also, the other challenge is doping. As I said, in transistors, you need to make source and drain. And source and drain in silicon transistors is enabled by ion implantation. But in 2D materials, you cannot dope them by ion implantation. It's a layer thick. It's only one layer thick. So as long as you think of ion implantation, you will damage the material. So you need to find clever ways of incorporating dopants during synthesis. And the other challenge is making contacts, good metal contacts for collecting holes. Kind of electrons are kind of solved because, and I'll show you how collecting electrons is kind of solved because it's very difficult to grow high work function metals, which is P-type contacts. So if you want to make logic, you need both P-type and N-type transistors. And the other outstanding challenge is high K gate dielectrics. So in the silicon industry, silicon oxide was the first dielectric, and then we moved from silicon oxide to hafnium oxide. And hafnium oxide was chosen for a given reason. There were hundreds of other oxides. Similarly, there's a continuous search for what is the ideal dielectric if you want to improve the performance in scale devices for 2D transistors. And especially I'm going to talk about these last two contents in terms of contact engineering and dielectric engineering, and how interface interactions play a key role in these last two topics. And we have recently, I mean, this paper will come out very soon. You can have a look at it, which summarizes these 4 critical challenges that remain to be addressed in 2-dimensional transistors. So what I'm going to talk about today is the first, to follow up on the technique to make van der Waals contacts. I will introduce what van der Waals contacts are and how they are ideal for, how they are different from 3D contacts to 2D contacts, and how these van der Waals contacts can enable, which we accidentally discovered, can really help us do spin injection. And lastly, I'm going to talk about some ferroelectrics, ferroelectric 2D materials, and how the dielectric semiconductor interface, or in this case, the ferroelectric semiconductor interface, plays an important role in controlling the properties of their devices. So the first thing, why do we need good contacts? As I said, we have a schematic here of a monolayer like PMD, which is like MOS2 or a WS2 material. And when you evaporate gold or titanium or chromium, all these metals using electron beam evaporation or thermal evaporation, this is a nice scheme from Shangping Duang's group. They show that when you evaporate it, you really create a lot of damage because these are energetic ions which get evaporated and they have high kinetic energy. And when they hit the surface of this one-layer molysulfide, you naturally create a lot of defects. And this is a TM image. You can see that it really goes through the material. And what these defects do, they pin the Fermi level. You're no longer free to use the Fermi level of the metal, but rather you have something mid-gap states between the metal and the semiconductor. And these defects are very prominent for 2D materials specifically because in bulk materials, you have an interface and then you have the bulk. But in 2D materials, you don't have a bulk. The surface is kind of the whole material. So if you damage the first layer, then you have nothing left. Manisha's group, when I joined the group, they were pioneering a technique which showed that you can make van der Waals contacts. Now, what do we mean by van der Waals contacts? It means that if you choose the metal such that the metal has a very low melting point, like indium, what you can evaporate it very easily. And when it evaporates, it has very low kinetic energy. And it can form a very clean interface with the molysulfide. And why do we call it van der Waals? We were asked this question a lot of times, why do we call it a van der Waals contact? What they did was they performed electron energy loss spectroscopy yields on the sulfur, which is, let's say they took many layers of molysulfide, and they did electron energy loss spectroscopy at the sulfur atom, and they looked at the interaction of the sulfur atom with its neighboring sulfur, and that was like a van der Waals interaction, how you would expect in pristine MOS2. And they also looked at the sulfur, which is very close to the metal, and that had a very similar interaction. So there was no evidence of chemical interaction between the metal and the sulfur. So it was more of a van der Waals-like interaction that you would expect between individual layers in the 2D material. And that is why we call them van der Waals contacts. And there's a van der Waals gap between the metal atom and the semiconductor of around 3 angstrom. And what this does, it helps us avoid any diffusion or any defects at the interface. And this is a field effect transistor, which shows that when you apply the gate voltage, you can switch on the device. And if you use a metal like titanium, which most people use, titanium forms a good contact because it has low work function. But the on current is much lower because you have a lot of defects and you lose a lot of carriers, and the carrier properties are degraded underneath the contact. But when you have these van der Waals contacts, you can really boost the on current and they improve the device performance. Now, this paper was published in 2019, and we were still wondering why does indium form van der Waals contact? What is the difference? So when I joined the group, I was co-supervising with Manisha, PhD student, and we started a small project where we really wanted to know how do these van der Waals contacts grow on the surface of 2D materials? So this is a very general schematic of how do metal contacts grow. So when you deposit a metal atom absorbs, and these atoms move around the surface of the 2D material, and they need to nucleate at a certain point. Now, where do they nucleate? Where would atoms nucleate? Atoms generally nucleate if there's a defect or there's an impurity or there's some particle on the surface. because there are no dangling bonds, the nucleation density in principle should be very, very low. And you should be able to grow large films. But when you grow metals like titanium, you create a lot of defects, and these defects act as nucleation centers. So you can see that when you grow like non-van der Waals contacts like gold or titanium, when you deposit them, you create a lot of defects, and each defect acts as a nucleation center, and you start growing these island-like growth. But when you grow materials like indium, which have very low kinetic energy and you don't cause any defects, you can grow large growth, and you can have like a 2D growth of the metal film. And we did some calculations of like for indium, what is the nucleation density? You can just do an AFM or an SM image and calculate the number of grains. I'll show you some images later. For indium, for example, on silicon oxide, you can see that we have like 426 per micrometer square grains, while for MOS2 and graphene, it's relatively reduced because the surface of MOS2 and graphene is much flat when compared to silicon oxide. This shows that in some AFM images, where you can see that this is, I think, 2-layer MOS2 on silicon oxide, and we have grown 5 nanometer indium. And this is just a topography of the image. And you can see that the indium forms really small particles on silicon oxide, but when it grows on MOS2, the grains are much larger, and they grow like laterally because there are less defects. And if you increase the thickness of the MOS2, you just make, and I mean, you can see that if you increase the thickness, then the RMS roughness, bulk samples have lesser RMS roughness because they don't feel the topology of the surface anymore. And as a result, the mean grain size increases a lot, and the density of these grains reduces as you increase the thickness of your sample. Now, this shows us what is the growth morphology of these contacts. And the other key point was like, as soon as this work was published, many groups started to make van der Waals contacts with other materials as well. And one of the key works which got published was from bismuth, which was from Jing Kong's group in MIT and like some people in TSMC, which showed this is a plot of contact resistance versus the carrier density of the various metals. And indium gold was somewhere around here. So you can see that it's not the lowest contact resistance. So now the community accepts that you need to make van der Waals contacts if you want to have good devices with 2D materials, because you want to reduce the interaction. But one of the main problems with van der Waals contacts is you have now a gap between the metal and the semiconductor. Ideally, if you want to improve current, you would want to reduce this gap, because this gap is like a vacuum gap, which is like a tunnel barrier. So this gap will cause electrons, will act an additional resistance. But if you can somehow reduce this gap and bring them more close to the sulfur, then they will have higher electron injection. But what we want is them to be very close, but not to damage them. So people showed that with bismuth and antimony, and people have almost hit the quantum limit for contact resistance. But our case was not that low. We had a certain finite resistance because the gap was around 3 angstroms. And we were thinking, what else can this be useful for? So we have now made a contact where there is a gap between the metal and the semiconductor. So to summarize this part of the talk, we can show that van der Waals contacts have a unique 2D growth morphology, and they can improve charge injection. We were thinking, can we use these contacts to improve spin injection? And I will show you why spin injection is a problem. And so I'm going to the second part of the talk where we're showing spin injection in graphene. And why do we care about spin injection? Because as I said, we are working for low energy electronics and electronics that consume low energy. Spintronics has been promised for the last 15 years that it can realize low energy electronics, because if you have pure spin currents, they would not dissipate Joule heating. And there have been a lot of, people have used a lot of materials to demonstrate spintronics. Very recently, two-dimensional materials are also being proposed as important contenders in this field. I mostly work on graphene, and graphene is, I'll show you why graphene is interesting. This is a nice schematic which shows what are the various kind of spintronic devices you can realize using 2D materials from using like TMR kind of devices, which are rely on magnetoresistance, to also devices that just carry spin to realize spin logic instead of charge logic. But all of these devices in spintronics are founded on the idea of GMR. And just to remind you, what is GMR? GMR is a phenomenon which was discovered, I think 20, 30 years ago, where people showed that if you have two ferromagnets, and if you insert a non-magnetic layer, then the resistance of these of this channel between the two ferromagnets depend on the alignment of the spin. So if you have, let us say, a parallel spin orientation, you have one resistance state, and if you have anti-parallel spin orientation, you have a different resistance state. And this is the foundational idea for most spintronic and magnetic devices which have progressed over the last few decades. And we wanted to work with graphene because graphene is a very good medium. So if you want a spintronic device, you want a material in which can carry spins, because that will be your spin channel instead of a charge channel. And copper, aluminum, silver, all of these materials were being used for spin channels. But graphene, in 2007, Professor Bart van Wees in Groningen, their group showed that you can really use graphene for very good spin conduction, because graphene has very long spin lifetimes, and graphene has very long spin diffusion length. And this stems from the fact that graphene has very low spin orbit coupling. It is made of carbon, and you cannot really flip the spins in graphene very easily. So what we are making is these devices called lateral spin ball. So this is a very test device where you just put two ferromagnets. You put two ferromagnetic contacts on graphene, and with an external magnetic field, you align these ferromagnetic contacts in parallel or anti-parallel orientation, and you measure the resistance of the graphene. And you see if there's any difference in the resistance because of the spin orientation of the two contacts. Now, the challenge in this field is that it sounds very straightforward. You put two ferromagnets and you measure the resistance. But you have to introduce spins from this ferromagnet to graphene, which means that these contacts should have high spin injection efficiency. So we know that we have magnets like iron, cobalt, nickel, but these magnets have certain polarization. Like I think iron is around 40%, nickel is around 28%, nickel is cobalt is around somewhere in between, which means if you have 100 electrons, only 40 of them would be spin polarized. And when you introduce them, you want to ensure that most of the electrons which are introduced still remain spin polarized and are not scattered at this interface. So it has been shown that if you just deposit a ferromagnet, ferromagnets by their nature are quite chemically reactive. Cobalt, nickel, all of them react very quickly. And they often react with this metal, and these reactions, and this which gives rise to very low resistance, and this can scatter the spin. And when the spin gets scattered, they would rather stay in the ferromagnet because they like staying in ferromagnets, and they would not be introduced in the channel. Rashpa in 2000 proposed that you can actually introduce a tunnel barrier. And by introducing a tunnel barrier between the ferromagnet and graphene, you can introduce spin by spin tunneling. And once they tunnel through, they can quickly propagate through the graphene, and the spin scattering is reduced dramatically. And this was the major breakthrough, which showed that you can actually see these initial papers from Bart van Wees and Albert Ford, where they show that you can introduce spins in graphene, and even in room temperature, these are low temperature, but they also show that at room temperature, you can carry spins in graphene. And this is what I was saying, you can apply a magnetic field and you measure the resistance. And when the spins flip, you can see a resistance peak due to the anti-parallel or parallel orientation of these two ferromagnetic contacts. And you measure a resistance, you measure a magnetic resistance around 1 to 2% across a graphene channel. And in this case, they use like 1 nanometer aluminum oxide tunnel barrier to introduce this to act as a tunnel barrier for spin injection. Again, as I said, like when you make devices with 2D materials, you have to take into care their nature and cannot just mimic what other materials have used. Now, this is in principle a nice device, but the main challenge is it is really hard to make these devices, because if you want to deposit a tunnel barrier should be less than a nanometer thick. But growing 1 nanometer Al2O3 on graphene is a real challenge, because graphene is very flat, you have no defects or you have no dangling bonds, and you really cannot make these atoms nucleate. So when you create these films, they are full of pinholes and defects. So you cannot grow very nice continuous atomic dielectrics on 2D surfaces. So if you want to grow them continuously, you have to make them thicker. So here they have used 1 nanometer. But if you insert a dielectric which is 1 nanometer thick, you can see the device resistance increases to hundreds of mega ohms. Graphene should be quite metallic. It should be in kilo ohms resistance. But introducing this layer makes it hundreds of mega ohms. If you make a device which is hundreds of mega ohms, it will really slow down your entire circuit. It's not really useful. So we need to make devices that will be efficient in spin injection and also low resistance. Recently, people have kind of given up on growing thin dielectric because it's really challenging. And what people are saying that they can use hexagonal boron nitride. Hexagonal boron nitride is an insulator, it is layered, and people insert these insulators between the metal, and they're using these insulators as spin tunneling medium. But again, this is not a scalable approach. You can only make devices by dry transfer in the lab. We wanted to see if there's a way to make these devices in large scale through a method which is compatible. And here comes our idea of van der Waals contacts, because we want to address this difficulty to grow uniform tunnel barriers of high contact resistance. So we were looking at how, because spin tunneling or tunneling is not a new phenomenon. Tunneling has been studied long ago. And this is like the old paper from Binning in the 1980s, where they actually showed that, first showed that you can tunnel through a vacuum gap. So you use an STM tape. I saw some nice STMs earlier in the department. And in STM, what you do is use a vacuum gap to tunnel. And people have also shown spin polarized tunneling through vacuum gap. In this paper, what they show, that if you use a ferromagnetic tape, you can actually introduce spins. And this is the displacement. If you change the distance, so this is around 3.5 angstroms. If you change the displacement by around 0.1 or 1 angstroms, you see an MR or spin asymmetry of around 1%. So it is in principle shown that you can use a vacuum gap to introduce spin, but this has not been shown in a device so far. So what we thought, we can make we can use these van der Waals contacts of graphene, where we have this vacuum gap between the metal and the semiconductor, which is the van der Waals gap. And we want to use this van der Waals gap just to introduce, as a barrier to introduce the spin. And we don't use any tunnel barrier, because tunnel barriers are really high, really hard to grow on graphene, because graphene is really flat. So we make these lateral spin balls in our lab. We just use mechanically exfoliated samples because these samples are of good quality. And first we deposited cobalt, which is a pure, which is the ferromagnet, which is, as I said, it is very reactive. And you can see the interface is highly disordered. And if you deposit indium cobalt, you can see it forms a very clean interface. And it is like a van der Waals contact with a vacuum gap between the metal and the semiconductor. And we also use Raman to test our devices. You can deposit very thin electrodes, and you can measure the Raman from the top. And you can see this is the Raman spectrum of graphene, which has two characteristic modes which are related to its band structure. And if you deposit cobalt, we see that this mode splits up and gives rise to a very strong defect mode, which is related to chemisorption of metals. And this also causes a change in some people have shown that from this Raman, you can calculate the change in carrier density of graphene as well. So we can see that pristine graphene has a carrier density of 10 to the power 12, but when you deposit cobalt, the carrier density underneath the cobalt really increases, which makes the contact very conducting, which is bad for spin injection because the spins would scatter if there are a lot of spins carriers. But when we deposit indium cobalt, we can form a van der Waals gap, and the carrier density is very similar to pristine graphene because we don't have this chemical reaction at the interface, and the interface is quite clean. And you can you have kind of this vacuum gap. What do we do magnetotransport? First of all, we do MOC to measure the magnetic hysteresis loops of these devices, and we see square hysteresis loops for our electrodes, which is governed by the shape and isotropy of the magnets. And you can do magnetotransport. This is the magnetic field versus the resistance. And with pure cobalt, we just see a change of around 3 ohms, which is very little. But with indium cobalt, you can see a change of around 50 ohms. And this high spin injection is enabled, and this increase is determined by the amount of spin injection. And this is due to the fact that now we have a tunnel barrier due to this vacuum interface between the metal and the semiconductor. This is just magnetotransport, but if you want to show, as I said, pure spin transport, you have to do something called non-local measurement, where all of this is two-terminal measurement. You apply you apply voltage and current from the same terminal. But if you want to do, if you want to measure pure spin currents, you source current from first 2 terminals, and the spins diffuse from the second and third, and you measure the voltage across the other terminals. So this is called spin diffusion. And even with spin diffusion, you can measure these MR, which shows that this is not charge-related phenomena, but purely spin-related phenomena. And if you apply a field which is out of plane, what happens when these spins are propagating? The spins experience Lorentz force, and they start precessing, and eventually they decay. And with these measurements, you can calculate the spin diffusion times. This is the test to show that what we're observing is spin diffusion, not some spurious effects related to charges. We also benchmarked our samples. As you can see, that these are the various materials that people use for spin injection. These are oxide-based tunnel barriers. These are 2D-based tunnel barriers. We have the van der Waals contacts, which have low contact resistance. And what I wanted to show is that, as I said, it's really challenging to grow these materials, to grow these dielectrics. So all papers in the spin injection community report their devices on 1 or 2 devices, because I'm not saying it's not reproducible, but it's difficult to make high yield devices. For the first time, we show like statistics, which has become very common for electronics, but it is not so common for spintronics. We are showing that you can actually reproduce these for more than 70% of your devices, because it's a very scalable technique to just electron evaporate van der Waals contacts, and without the need for growing tunnel barriers, you can reliably introduce spins. And we obtain MR, which is not obviously record high, because people have shown using LSMO and other materials with very high spin polarization that you can introduce higher magneto resistance. But again, the contact resistance is very high, which is practically not feasible. So we have a sweet spot where we have decent, reasonable MR, which is quite consistent with previous reports, but also low contact resistance. So summarize, what we can show here that we can use these van der Waals contacts to form that to enable direct spin injection without tunnel barriers that are really hard to grow on 2D materials. And this is a facile technique to reproducibly achieve spintronic devices with low contact resistance. And in the third part, I'm going to talk about ferroelectric affinities. I'm going to move from contacts to dielectric interfaces. And ferroelectric affinities are becoming quite promising because they offer opportunities for non-volatile storage and computing. So it is like it can really help. It can really help realize things like in-memory computing, which are quite important for which can reduce the number of devices we need to process a lot of data. Sorry for this pixelated image here, but this is a classic ferroelectric. I mean, you guys might be familiar with what is a ferroelectric. Ferroelectric is a material which can have a bistable state due to two electrically switchable stable polarization states. And these two states can be used for non-volatile control of charges in a semiconductor. And people have shown that if you can use this, if you can replace the dielectric in a gate with a ferroelectric, you can achieve like a memory, because now you kind of mimic the histories of the ferroelectric in the charge transport, and you can store information along with processing information. So it's like a logic plus memory device. Now, although this looks quite promising, there's a lot of problems because ferroelectric and the interfaces are always a huge a huge problem when you look at the effects of ferroelectrics. The university have been working on ultra-thin ferroelectrics a lot as well. And as you reduce the thickness of these ferroelectrics, the interfaces play a huge role, and they can really change what you observe in your devices. So there have been hundreds of reports where you see loops, but all those loops don't mean ferroelectricity. They can be due to defects or traps or residues. But so we wanted to study what happens when you put ferroelectrics and semiconductors together when you have van der Waals ferroelectrics. So the van der Waals ferroelectric, this is a very classic van der Waals ferroelectric. It's called copper indium thiophosphate. It sounds very complicated, but basically it is a sulfur octahedra where you have copper ions, and the two polarization states in the ferroelectric are attained when you can electrically switch the copper from the upside to the downside in the lattice. Now, the copper ion here is quite mobile. It's like an ionic semiconductor, which makes it very interesting because you can also switch the ferroelectricity, but with field, you can also make the copper ion move around. So it's kind of an ionic semiconductor and a ferroelectric, which makes it like a ferroionic material, which makes it quite difficult to understand which is it the ionic motion which is giving rise to memory? Is it the ferroelectricity giving rise to memory? So we wanted to understand what is the contribution from these effects in our devices. These are standard PFM microscopy loops where you can see the ferroelectricity in these crystals. These are the phase and amplitude loops. So the goal of this project was to look at when you place SIPs or a ferroelectric on a semiconductor, does it dope the material? What happens to the interface? And there have been a lot of reports with SIPs on MOS2, SIPs on WS2. But we feel that graphene is a very, very nice, easy material to work with because graphene can really help you sense both electrons and holes to select unique band structure. So graphene can be electron doped, can be hole doped, and if you apply gate voltage and if you measure the resistance, you can see this Dirac peak. And you can see that this is the electron doped region, this is the hole doped region. So if SIPs dopes graphene with electrons, you would see some changes in this resistivity versus gate voltage in this plot. So to understand this, what I was saying that if you p-dope graphene, you would see the Dirac peak shifts toward positive voltages. If you n-dope graphene, you would see the Dirac peak shift towards negative voltages. And we wanted to see what happens when we put SIPs on graphene. To understand what happens, first we made a very standard FET. So let me explain this device. What we have here is a graphene transistor with a silicon oxide backgate. So this is a very standard graphene transistor. And we want to use this graphene transistor to sense what happens when you put something on top of it. So we first put an HBN device, just an HBN, which is an insulator. We know that it does nothing other than just being a dielectric. So we take a graphene plate, we make two devices. On one we put HBN, on one we put nothing else. So it's bare graphene and HBN encapsulated. And we apply a gate voltage from the back. And we just measure the resistivity. And we see the bare graphene has like a Dirac peak around 0 volt, which is like the standard graphene as you would expect. And when you encapsulate with HBN, HBN somehow reduces the contaminants on graphene, which cause like water and other molecules of graphene can make it quite p-doped. But when we put HBl, we just reduce the contamination and we see like increase in the resistance, which is quite standard. We don't see anything funny happening here. But when we put SIPs, which is the ferroelectric, interestingly, we observe that apart from this main Dirac peak, we observe a shoulder peak at around negative voltages in graphene. Now, this is, we're not the first people to see a second peak like this. What this indicates is that when you're in the negative voltage range, which means when the graphene is kind of carrying holes, you see an additional peak, which means the graphene must be doped with electrons. So you form like a p-n junction in graphene. So you can see that the SIPs does not cover the entire graphene channel. So we think underneath the SIPs, it is somehow changing the local doping environment. And the regions outside the SIPs are still p-types, so it forms kind of a p-n junction. You see this additional peak. We are very scared to call it a Dirac peak because we don't have evidence to call it. We don't want to call it a second Dirac peak right now, but we see a resistivity peak. But why do we have this peak? How can we correlate this with the properties of SIPs? As I said, SIPs is an ionic conductor as well. It has copper ions. And people have shown that if you increase temperature, the motion of these copper ions in this material changes. So we did temperature dependence of this resistivity. And you can see that the second peak is strongly dependent on temperature. So at 50 Kelvin, the peak is quite far away from the main Dirac peak, which shows that this doping effect which we have is quite pronounced and localized at low temperatures. But as we increase the temperature, it kind of, the doping kind of becomes more delocalized, and you can measure it in the main graphene channel and we move closer to the main Dirac peak. And this is like just extracted from this graph. This is the threshold voltage minus the backgate. You can see that the second peak is coming closer to the main Dirac peak as you increase the temperature. Now, what does it have implications? So the main goal was to understand that you have this phenomenon, but what happens when you put a ferroelectric on graphene? How does it affect the property of devices? Because when you make ferroelectric FETs, we often see loops which are funnily shaped, which are asymmetric, which are non-uniform. But we wanted to understand what is the regime in which you should operate these devices to harness their properties more effectively. So for that, we made a ferroelectric FET. In previous device, we were using the bottom silicon to gate our device. Now we are just changing the wiring and we are getting the top. So now the silicon is backgated, but we are using a gate voltage on the top. And we see when we use HBl, which is a dielectric, you just see a normal Dirac peak because that is just dielectric. But when you have used the ferroelectric, you can see two bistable hysteretic loops. And these two loops are due to the two polarization states in the ferroelectric. This is a ferroelectric FET. And the two loops here occur due to the polarization switching in the material. As I said, that the ferroelectricity is strongly correlated with the ionic conduction. And when we do temperature dependence on the ferroelectric FET, we can clearly see that the loop changes shape dramatically. You can see 50 Kelvin, the loops are very asymmetric. And often people measure such loops in room temperature as well, and they don't understand this. And here, through a systematic study of the SIPs characteristics at function of temperature, where it is known that how the copper ion migration takes place, we show that as you increase the temperature, the loops become more symmetric because now the doping is not localized, as we show here. It is more delocalized, and you can make the entire channel n-type, which is reflected because both these Dirac peaks now move towards negative voltages, which suggests electron doping in the system. So we feel graphene FETs can act as a sensor to understand ferroelectric properties of not just SIPs, but also a lot of other ferroelectrics which are emerging, such as the Moire ferroelectrics out of twisted TMDs and twisted boron nitride. It's an interesting way to understand what is happening at the interface. In this case, which is due to copper ions. In other cases, it could be due to Moire potentials that are generated when you twist these heterostructures. So to summarize, we have used graphene FETs to sense interface effects in van der Waals ferroelectrics. And we show that when you put SIPs on graphene, it can really electron dope graphene, and which affects the properties of their devices. So what we're moving forward, so I showed you some key results that we can actually make these contacts, van der Waals contacts, which can enable spin injection, and we can make very nice ferroelectric FETs. So now we are trying to couple spin with ferroelectricity, and we're trying to make multi-ferroelectric devices. Because if you can now control the spin transport through ferroelectrics, you can generate 4 readout states instead of 2. So in ferroelectric FETs, you have 2 states with 1 polarization due to the 2 different polarizations in the ferroelectric. But if you have spins, you can have 2 more states with the spin. That was the idea of multi-ferroelectrics and oxides. So we want to create multiple readout states. And also, as I said, this is an ionic conductor. You can actually stabilize the ionic motion very carefully with voltage, and you can generate devices with multiple readout states, which are really interested. People are interested in this for analog computing, which is promising for neuromorphic applications. So we're trying to look at multi-ferrite devices and ferroelectric devices with multiple readouts. I think with that, I will stop, and I'd like to acknowledge some of the key people, Mahira, who's a PhD student I'm working with, and Jan, who initially pioneered the van der Waals contacts, and Manish, Peter Newton, who helped us with the MOC measurements, and our collaborators from UNIST in Korea, who helped us with the TM measurements on our samples. And I'd like to thank all of you for your attention, and I'll be happy to take any questions if you may have. Thank you so much.
Really very nice talk.
Thank you.
I have a question regarding the synthesis of these van der Waals.
Yes.
So, I mean, when you increase the temperature of aluminum dioxide, which I assume you need in order to grow this in top, you create basically defects inside.
Yeah. So the way we deposit them
so
is
how it works?
so we use electron beam evaporation, where we have a substrate which is at room temperature. And we just use electron beams to evaporate out of a crucible. And the electron beam energy determines the kinetic energy of the evaporated atoms. And by the time they reach the surface, we need to ensure that. So the trick is that we need to have an evaporator with either large working distance, where the evaporated atoms are not very hot when they land on the surface. Now, when you deposit gold or titanium, the evaporation temperature is slightly higher, and these hot metal atoms will cause these defects. But in India, because the evaporation temperature is very low, around 150 to 200 C, so the kinetic energy is very low, and it does not create the defect. Yes.
I have a question related to this. So very nice work, very nice talk. So regarding this evaporation of indium on top, I guess before that you do also the e-beam lithography or lithography. So did you observe any influence of this, let's say, polymer residues on the surface prior to the evaporation? Because I mean, you cannot really clean the surface, right? I mean, that's
I mean, of
so
course.
how does it influence this resistance when you actually create one of those contacts?
I mean, nothing can be 100% clean, right? But we use for these devices we use PMMA, which is quite which reasonably gets you very clean surfaces if you can develop them clearly after the lithography process. I think if you have more residues in your at the interface, you would act as nucleation sites, and that would give rise to like that 3D growth which I was talking about. So the deposition has to take place in ultra-high vacuum, and to answer your question, we do not use any additional step to further purify. We just use standard development procedures and ensure that the evaporation takes place in ultra-high vacuum. And we have not seen any predominant effects of like these residues on the growth, because we think that the residues are really not what is causing the damage. It is the evaporation of the metals and the kinetic energy of these metals which is causing the damage, causing the defects.
Did you ever try to, like you were showing this paper, when they transferred metal PDMS?
There was one.
Try that, and how does it compare to?
We have not done transferred contacts, but I think the current values are quite similar with them. I think one of the key the current also depends on the substrate as well. I'm not sure I don't remember what substrate the transferred contacts guys use. But it's mostly to do with the work function. I think they use silver, and we use indium. The work function can really also align the formula because the main idea is when you use these van der Waals contacts, you are really able to use the work function of the band, and that is what determines the performance of the field effect transistor. But we have not transferred contacts, and we have not compared it. But in terms of what they have published, it looks quite similar in terms of the output.
Yeah. Thank you for a very informative talk. Maybe a bit blunt question related to your first slide.
Yes.
Now, as I'm listening about superior properties of graphene started 15 years ago, my postdoc at Chalmers University, where graphene flagship project was conceived. and you said that you are into making devices.
Yes.
Now, can you tell me? You didn't show the spatial scales of your devices, but if I correct one or two slides, it's like 1 micrometer of the order of magnitude. So, do you really believe that this technology, even in principle, can compare to 4 nanometer silicon-based technology with perfect 100 billion transistors?
Of course. We do. We are. I mean, first of all, I think in terms of graphene, I think I actually visited Chalmers like last year with Saroj Dash's group, who are working on very similar ideas. There's a reason we have used like large distances here, because we want to show that graphene can actually we can show spin distribution across micron lengths. So in this case, graphene will use as a spin conductor, not as a processor. So you just want to use graphene as like an interconnect. Yes,
perfectly correct. I don't doubt.
You
said.
So, but I think your question is related to semiconductors. Yes, your question is related to your question is related to semiconductors. In terms of in semiconductors, we're not using graphene, we're using MOS2, and in principle, it is not. I mean, if you ask me today, I would not hedge my bets on having MOS2 on my smartphone in the next 10 years. But I think it's very important for us to work on techniques that would make these materials come closer to technology. So I think the oxide community has been realizing this as well. And there's a lot of work on amorphous oxides, for example, now, because they think amorphous oxides are more compatible to like existing technology. So the main message I wanted to say that we have hundreds of materials and people are working on materials with exotic properties. But it is not fair to just say that this material will replace silicon. But I think we have to identify what are the problems it is with these materials that are stopping it to come closer. And our effort is towards understanding how we can make them more compatible and to send a message that using the same techniques that you use for silicon will not help you. Because we have techniques like ion implantation, which people use in silicon community, but that will make your case even worse for these materials. So you need to identify techniques and methods which are compatible with these materials and not silicon. And to answer your question, if it will replace silicon, I don't know, but we can say that we can at least post complementary functionalities. For example, 10 years ago, no one thought that we could convince TSMC to at least try these. Right now, the main challenge is growing these in large scale and transferring them. And I think I went for a talk by Juliana Radu, who was actually showing how they have pioneered this transfer technology. And they were initially doing it in IMEC. I think they're at least willing to try and they're willing to see, because we have seen a lot of changes in silicon as well. From silicon, they moved to strained silicon. From strained silicon, they moved to high K. But the main backbone has been still the same. So we need to give them solutions that they can somehow use and not ask them to change everything. We cannot introduce techniques that are 800 degrees, for example. So it is very difficult to change a $1 trillion industry, but we can at least give them some alternatives which they might be interested in and not just like rule out on the first meeting.
So I have a question about these electronic devices that you made. So the proposal by Rajba to introduce additional layer, I understood initially it should be an insulating layer to enable this
connectivity in space
tunneling. Yes. But in your case, you have indium, which is a metallic layer. Yeah?
Yes.
So you can also have, I mean, the scattering of spins could also happen at such interface, but in your device somehow it does not.
Yes, so I think one of the key things is like here, what we do is if indium is a very soft metal, and you deposit indium, and when you deposit cobalt, and we have, I'm not sure, I don't have it here, but I think I have my supplementary slides. We also did like EDX spectrum here to identify the atoms. So when you deposit cobalt has a higher kinetic energy and kind of alloys with indium. And at the interface, you have an indium cobalt alloy with a lot of cobalt. So we don't have pure indium at the interface. We have majority cobalt at the interface.
So it's not a tunnel barrier. Right?
So the vacuum gap acts as a tunneling barrier. So for example, if you look at the boron nitride work, the boron nitride thickness is around half a nanometer, and it gives you a tunneling barrier. So we have a thickness of around the same range. And Rashba's plot actually shows like a Lorentz curve, which shows that you have a nice range in which you can see the tunneling, which is around few kilo ohms. And if you make it very resistive, again, you cannot see it. So we want to be somewhere near that resistivity peak. Of course, if you can make this tunnel barrier slightly higher, maybe by somehow controlling the growth, you can probably see some higher spin injection at the cost of contact resistance. But we want to somehow optimize the contact resistance and also spin injection.
Okay. And just short related question. So you somewhere in your results show that you have 2 to 3 micron spin diffusion lengths. Is this because of the size of the device, or this is?
It is because of the size of the device, and also because of the quality of graphene.
Because theoretically it should be 100.
It should be 100. I mean, if you have epitaxial graphene on like silicon carbide, people have shown that you can really make very long spin diffusion lengths. We have not tested such quality graphene samples, but I think in principle it should be possible. I mean, yeah, they're just limited by the device.
Okay, so we thank Soumya, I guess. Yeah.
Thank you so much.